Okay, I think we'll get started. So this is the next lab in the 12F1822 series, and we'll bring you starting up this is the first of a few labs dealing with pulse width modulation. So what's neat about this PIC is that it has as a peripheral pulse width modulation capabilities. So that will run outside of the central processing unit of the PIC. You'll be able to just have it running independently, which can be very convenient. And so what we're going to do is just a very, very simple setup where we are going to just have the PIC acting as a timer, and we're going to be shooting for about 20 kilohertz, and very, very simple setup. We just power the PIC and then send pin 2. We're going to set up pin 2 as the pulse width modulator, so we're going to set it to its PA1 mode there, and that'll just generate this outside of the program. So the program will be very simple. Could even be, this is almost the simplest it can be. Wouldn't even need this no op. And we'll just loop around in a circle here. And what you'll notice here is that none of the program is not doing anything to cause the pin to go on and off. So we're not bit banging this like we would have to do if you did the PIC 10F200, the simplest of all PICs. If you did that series with us, doesn't have the pulse width modulating capability, so you could do pulse width modulation, but you would have to do it inside the program. All right, well, it's a little, it looks like a little intimidating when you're looking at the manual and you're trying to figure out how to do this, because it involves a lot of registers and you're moving a little bit back and forth between the different banks as you set this up. The data sheet is pretty good at kind of taking you through the setup, and so we'll just do that. So the goal here is to kind of walk through the setup, make sure that we can get it going. We'll look at the pulses on the scope. We'll control the duty cycle of that. So let's get to the computer. Okay, so here we are. The PIC is set up. I have an LED here. I didn't draw that on the board. It's just to kind of let us know it's on. And we'll actually see it kind of fade in and out as we're going to change the duty cycle. So if we have a mostly off duty cycle, then it will be dimmer. If it's mostly on, it will be brighter. So kind of as an indicator for us, but we'll be looking at the scope to see this. All right, so let's get ourselves set up here. So I've got the MP Lab set up, so we'll do a new project, and microchip embedded. I'm going to just use recently used and 1822, and then make sure that we use a PIC kit 5. So I've got a PIC kit 5 here, and go next. Here, don't need anything there. Then we'll be programming in assembly, so we'll choose the assembler, not the C compiler. And then we'll give this a project name. We'll call it just Pulse Width Modulator Test 1. And we'll finish that. Okay, and you can close this. We'll set up under source files a assembly file, and we'll just call that main. And we'll now go out to my GitHub, and we'll grab it here under the PIC12F1822 repository, and we're going to do the pulse width modulation. And so I'll just copy this, come back over, and paste this in. Okay, one quick thing here. We will go to setup, and we will power this. It's a very simple circuit, so we'll power this with the PIC kit 5. So we'll choose PIC kit 5 here. We'll choose power, and then we'll turn that on and apply and hit OK. All right, so we're all done. I'm going to just build this and then run it, make sure everything is working. This will pop up to kind of protect your device. It can handle 5 volts, so we'll say yes, and go ahead, and looks like it's working. Okay, so now let's see what's going on here. So we're going to kind of be flipping back and forth for the moment on the data sheet. Whoops. And I'm going to go to page 10 first, just to show the pin configurations. So we're going to be looking at setting this up on RA2, and so we're going to be using PA1. So of all the different things it can do, just GPIO, then analog or A to D, and comparator and all this, but we're going to be down here with the pulse width modulation output. So we're setting that up for this. And so that's going to be done with the tris as an output, and then some of the other registers that we saw on the board there. Okay, so let's go now. It starts talking about this in page 195. So this starts with this overview, and what we're looking at here is we're going to set the period, and then we're going to set the width within that period, so we can control both the frequency or period of the pulse width modulation signal itself, and then within that we can control the duty cycle. And so I'm going to go down to the next page here, page 1, and I'm going to maybe make this a little bit bigger. Okay, so let's walk through this here. So you could follow along on the data sheet, and let's go to our program here. So this initial stuff, this is all just the configuration bits that we've been using throughout the period. So let's get down into our main program, and here's where I've broken this up like we usually do. So the main part here is just all the setup we have. So we've got a little bit of setup here, and then we're going to just have this main loop do basically nothing, just go in a circle here. Okay, so first thing we need to do is set the timer. So the pulse width modulation is going to be based off of the internal clock of the clock of the PIC, and so that can be anywhere up to 32 megahertz. And so this is the first part of that. And the previous lecture, Lab 6, we went through how to control this. We're going to actually set this to 8 megahertz, and we are going to do that because coming up, we're going to build off of this lab to do some heterodyning of ultrasonic signal to bring it down so that we can hear it. And so what we're going to want to do is, it turns out with this, we can hit a nice frequency to do that. So we're going to, that's what that is. Not critical to the pulse width modulation. This can really be anything, but once this is set, then you use it to figure out the period and the duty cycle. Okay, this stuff, not too much going on here other than what we always have to do here. So we're clearing the latches and the ports, and then the AND cell. So we're clearing all this. We're not going to be using the A to D. And then we get to the tris. So this is where we set things as inputs and outputs. So 1 is input, and 0 is output, and so we want this to be an output. And so here's a RA0, here's RA1, here's RA2, so it's set to a 0. So that allows us to potentially use the pulse width modulator. Okay, so now that's done. So that's the first step. So I think that's up here. Yeah, actually it isn't even on the steps yet. Okay, so now what we do is we go to PR2. So let's go back here, and so okay, yeah. So here's by setting the tris here. Now PR2, that's our next thing. So this is going to be our pulse width modulation period value. And so that's over here. And here is our, here's the formula for that. But I'm going to skip over here to the example. I'm going to use this. Let's see, where are we at? Yeah, 8 megahertz. Very easy to set that. That's why we did that. And I want to be around 20 kilohertz for a later project. So this is a nice one for that. And this gives the information here. And so the prescaler is going to be 1. So we'll talk about that in a bit. And then this value, this is what we write to PR2. So let's take this and let's go to oh, shoot. Let's go to hex. So hex 65 to binary. Well, let's do it to decimal first. So it's 101, and then let's do it to binary. And so this is the binary. So we'll use this in a bit here. So let's go back now. You don't have to use these. You could set this to anything you want, but I'm just going to try to hit this for our example. So let's go back to our period here. And so we're going to set this to 101. And so here's the formula to give us our period. 101 plus 1 times 4 times 1 over the clock cycle frequency. So that's going to be 1 over the 8 million, and then times the prescale factor. So let's do that really quick. So it's going to be 102, because it was 101 plus 1, times 4 divided by 8 million times 1. And we do that, and we get 51 microseconds. Okay. So that's our total period. So if we go up here, that's going to be the full period of this. Okay, so that's what gets set. That's what's getting set right here. So this is the binary. So let me go back to this. That's the binary 1100101, and that's what we put in here. 1100101. And so that gives us 51 microseconds for that. So we sent that to the working directory, then we move the working directory to PR2. So we have now put this binary in the PR2 register. So that's that's the register that holds the pulse width period. Okay, now what we want to do is we use, let's look at page 197, and we see here we need the prescaler of 1 here, and that's done. Go back up to the directions here. Well, let's see. That is done in the T2con register. So this is another register for us, and it is bit 2. So here's 0, 1, 2, and if it's active, then it sets the prescaler to 1. And so that's what's going on here. And so we move this bit 2 is on to the working directory, and then we write that to the T2con directory. Now we need to switch banks over to, because these are both on bank 0, the CCP1con. This is for the duty cycle information. And actually, the duty cycle is a 10-bit resolution. So it's going to use 8 bits here, the most significant bits, and then the 2 least significant bits are going to be in another register. That is the CCPRL1 oh, sorry, CCPRL1 is where we're going to put the pulse width, but there's the two least significant digits are on CP1 con. Okay, so let's look at what CC1 con, it holds more, carries more information than just the pulse width. The pulse width is set here mainly. The 8 most significant digits are here, and that's how we control our duty cycle. But let's go ahead and look at CC con. And I want to find this here now. I'm going to pause the video and find the CC con listing of what each bit is. Okay, I guess it was right there. So here it is. So bit 4 and 5 are the least significant bits of this 10-bit duty cycle. But what are the other bits? This is the mode. So we are going to, for our purposes, it's not going to matter too much. We're going to use this mode here, where PA1 and PA2 are active high, and P1B and P1D are active high as well. So that is setting the last 4 bits here to 1100. So that's this here. So that's bits 0 through 3. Then 4 and 5 are the duty cycle ones. So we're just going to set those to 0. So that means we're really going to just have 8-bit resolution. We're going to fiddle with this. We're going to change this to get our different duty cycles. And then the most significant bit, this is where we are putting this into pulse width modulation mode. So we're using 0, 0 here. And so if we look at what that means, we want just a single output. PA1 is acting as the pulse width modulator, and the other pins are just going to be GPIO pins. So that's what we're doing here. So that says that when we're in pulse width modulation mode, then this tells us what this activates that PA1 here. And you can see these other ones, they have different active and inactive, up to 4 of the pins. Okay, so that is what this registry is doing. And so we're going to move that to the working register, and then the working register to the CCP1 con and write this binary to it. Okay, so here we are with the duty cycle. So let's get this figured out. So this is what's going to be key for this, and you can write to this. So we'll be doing this in the next videos, where we're actually changing the duty cycle, and that's an important thing to do sometimes. So we'll do that. But for now, we're just going to set the duty cycle. We'll recompile this and rewrite it to the PIC with different values, so we can see how that changes things. But we won't have an active program where this changes. So you can write to this at any time, and then it'll just pick up. It'll just modify the duty cycle. Okay, so let's do that. Let's figure out what we need to do here. So we have to go back to 195, I think, and scroll down to the pulse width calculator. So we are going to use a binary number here, and the 2 digits here, we're going to always keep these equal to 0. And then this is our 1/8 million. and this is our prescaler, which is 1. So let's solve for pulse width. So let's, I'm going to bring up this Mathematica here. Our period, we said, was 51 microseconds. So what we're going to do here is we're going to take we want half, let's try to shoot for a 50% duty cycle, and then we'll change it after a bit. So we're going to take this period, divide by 2, and then multiply by our 8 million to figure out what we need here to put into our value for this. So 204. So let's go ahead and go and change, or let's do 204 to binary. So this is our binary. So let's copy this and let's go back and put this in here. Now, notice this is an 8-digit binary. Where were we? That's an 8-digit binary. We have 10. So what we have to do is these two are going to be, the last two are going to be in the other directory. So let's look at that. We're just going to leave those as 0, 0 all the time, and they happen to be 0, 0, so that worked out good for us. So that means we paste that into here, Control V, and then I got to remove these 2 zeros. These 2 zeros are really these 2 zeros. Okay, so we could always change those as well. So this should give us now a duty cycle of 1/2. And so what I'm going to do now is I'm going to I'm going to move the camera and put it on my scope. And unfortunately, the camera doesn't focus very well, but I think we'll be able to see everything we need to from that. So I'm going to just build this and run it, and then send it to the chip, and then I'm going to move the camera here. So I'm going to pause and then restart after it's all set up. Okay, so tough to see here because it just never focuses on here. But you can see I've got the 2 cursors here, and I don't have it perfect. Let me move those. Okay, so cursor 1 and cursor 2. The difference between those is 51.2 microseconds. So pretty much spot on to what we thought. You can see, I've noticed there is a little bit of jitter, so there's a little bit of instability, but not too bad. So pretty good square pulse here. And then let's look at the duty cycle here. So let me, let's see, let's go to cursor. I'm going to move this guy to here and look at the difference. So the difference there is 25.2. So pretty much exactly half. And that's what we got for getting that 204. So let me go back to here. And we can see here, this is that 204. This, and then these two are the 204. And we see this 50% duty cycle. Let's change it here now. Let's drop this down. Let's make that a 0. So this should decrease the duty cycle. So I'll go ahead and run this, and we see now the duty cycle is 10 microseconds. And so we could do this even more. We could turn that to a 0. And we should notice now, kind of hard to see because this just looks bright, all level brightness, but I'm guessing this will start to look dimmer too now, since the duty cycle will go down. But this will be a little dimmer. Yeah, it's definitely dimmer in real life. Probably not on the camera there though. so much. And we can take this even lower. And we just get these spikes over here. Likewise, we can go in the other direction. This will probably be almost all on. Yep, and here we have a much larger duty cycle, and I bet if I put that to be 1, we have almost all on. Okay, so that's how we can control the duty cycle. Okay. All right, so that's a good start with the pulse width modulator, and we will see here that we can use this in various ways through the next couple of videos in this series.